Here's our second installment in the explanations for the solutions to the protein purification practice problem set. So we're on question number 3, which is asking you to first view the video that was linked, and so hopefully you did that. It explained in detail the procedures of STS-Page and gel filtration, which on Tuesday's lab section we didn't have time to go through STS-Page, so you really need to watch the video to understand this. So the first question is, if your goal, is to determine as accurately as possible the molecular weight of the proteins, would gel filtration or STS-Page be preferable, and why? So here is, it's good to think about the purpose of each of these two techniques. One is a technique that's used for analysis, and the other is a technique that's used for preparation. So in this case, we want to analyze the mass of the proteins, the molecular weight of the proteins. So we would use the technique that is an analytical technique, and that is STS-Page. So STS-Page, is an analytical technique that is much more accurate in terms of the relationship between how far the peptide will move through the material based on its molecular weight. So it's an analytical technique that's much more accurate in terms of separation by size, but I'm going to put in parentheses here, but only a small sample of your protein will be used, and you can't really recover it at the end of the procedure. Is used, and protein is not recovered at the end of the procedure. All right, so then in the second case, for part B, it says if your experimental goal is to collect each intact protein, that's your goal, for further analysis, would gel filtration or STS-Page be preferable? In this case, gel filtration is going to be preferable. So gel filtration is a preparatory technique, which means that if your goal is to get a lot of material that has been purified and be able to use that for something else afterwards, that's what we mean by a preparation technique. So it's a preparatory technique where you take all of your sample, you use gel filtration to purify the sample and collect it for further use. So STS-Page you use for analysis because you run a series of standards so you can get you can take measurements and get the exact size of your protein, whereas gel filtration, it does separate things based on size, but it's not as sharp of a separation. You use more material, but you can collect. It has the advantage that you collect that material, so you can use that material for other things afterwards. Whereas with STS Page, the analysis uses up your material. All right, so the next question really has a lot of possible answers. I'll go through one of them so that you can see my thought process and my rationale for answering this question. Okay, so your goal is to separate and isolate 4 proteins from a cell lysate. Now this problem is kind of an artificial question, because normally, you have a mixture of things in your cell lysate, and you may only know details about the one thing that you want, but maybe you know about more things. But so this table is telling us, okay, let's imagine that there are 4 proteins in this mixture, and we know bits of information about them. We know things about their molecular weight, we know their isoelectric point, and we know a little bit about its function. Does it bind anything in particular? Okay. So this is asking us to design a scheme that would facilitate the separation of all 4 proteins. So what we want is we're going to make a flow chart, and the goal is to get all 4 proteins into 4 separate test tubes, say. Okay? All right. So we have things that have differences in molecular weight, differences in isoelectric point, and differences in binding characteristics. So these 3 categories of things just immediately bring to mind 3 different categories of techniques. So for molecular weight, let's do this. I'll write it below the column. So for molecular weight, things that separate by molecular weight, gel filtration would be a good thing to use to separate things by molecular weight. Isoelectric point, we could say ion exchange. Okay, and then binding characteristics, affinity chromatography. Because we have one protein, protein C here, that binds to this molecule called concanavalin A, and we do have a chromatography resin, an affinity chromatography resin that has concanavalin A on it in the lab. All right, so let's just take a few more notes. So I'm going to go back to the purification slides, and we're going to look up the gel filtration resins. Let's see. Whoops. Charge of protein, ion exchange. Here we go. Okay. So the purpose of when you make a scheme, you want to be as specific as possible as to what you would use. Okay. So I'm going to see if I may not be able to copy this. Let's see if I can copy it, and let's see if we can paste it into here. Oh, we can. Yay. All right. So I'm just going to paste this here so that we have the properties of the gel filtration resins. So again, so that when we look at the molecular weight sizes, we can choose an appropriate kind of resin. Okay. The other thing I'm going to do is let's go look at ion exchange. Okay. So if we go here, and this is the bit of information I want to take with us, okay, because it gives us the name of some resins. So we're going to paste that over here. We're going to make it a little smaller so it doesn't get in our way. All right. So now we have the reference material that we need to, to start making our scheme. So I'm going to make my scheme in red. All right. So I'm going to look at these and I am going to say, all right, I will start my purification scheme. And again, you can start any way you want, but I'm going to start my purification scheme with affinity chromatography. So step one, I'm going to do affinity chromatography. And I'm going to use a concanavalin A. Concanavalin A resin. All right, so what's that going to do? That is going to give me, in this tube, I'm going to have protein C, and in my other fraction, I'm going to have A, B, and D. Okay? All right, so step two is going to be, for me, let's see, so I have 3 things left, and those 3 things are something that's 80, whoops, that's 80,000 kilodaltons, one that's 40, one that's 48, and then I have 6.3, 7.8, and 6.2. So what I think I'm going to do is, because these 2 things have a similar isoelectric points, and B has a different one, I am going to do ion exchange for my next step. And what I'm going to do is, so remember, okay, if your pH is below your isoelectric point, your protein's going to be positively charged. Okay, so I'm going to say, if I do at pH, let's see, 6.8, then what is the charges of these going to be? Okay, well, my protein A here, the pH is above, so the pH of 6.8 is above the isoelectric point of protein A, so that is going to be negatively charged. So this will be negatively charged. Same thing with D, that will be negatively charged. But my protein B is going to be positively charged. Now remember that C has already been taken out of the mixture by my first step. Okay, so if I do cation exchange, it will bind the positively charged B. So that's what I'm going to do. So it's if I select a cation exchange resin, okay, so I'm going to do cation exchange with CM cellulose resin at pH, let's say 6.5. I'm going to, whoops, we'll do 6.8, sorry. That was what we said there. Okay, so what is that going to do? That's going to leave me with, oops, I should have made this arrow go this way. There we go. That will mean that my B will stick to the column and be eluted. And then what's going to happen is what will be left, or will pass through and not bind to the column, will be A and D. Now my last step is going to be, will be a separation of A and D, which are 80,000 daltons and 48,000 daltons. So if we look here, okay, our, I could use either, oops, that was kind of weird. What happened there? Just gonna fix that. All right, so I could use either Cefidex G75 or Cefidex G100 because both my proteins would be in that range, right? 48 and 80. 48 and 80 are both in range here. What I'm going to do though, because 80 is at the top of the range for G75, I think I'm going to go with Cefidex G100. So both of my proteins are within the range. Okay, so step 3 is going to be gel filtration with Cefidex G100, and that's going to mean that I will separate A and D, and they will wind up being in 2 fractions if I collect separate, multiple fractions coming off of the column. So that's one way of doing it. Okay, you could do these steps in a different order. You could do the gel filtration second, or you could do your ion exchange first, or you could you could move these around in any order, or maybe you decide you want to do anion exchange at a different pH. So there's lots of different ways you could do this, but this is one way you could do it. And I was trying to show you how you would be specific about what you would do. Not, oh, I'm going to do a chromatography step, or oh, I'm going to do a gel filtration chromatography. No, well, which of those resins would you do? And why would you choose that? Which pH would you do? Are you going to do cation or anion exchange? So again, multiple possible answers to this question, but no matter how you answer, no matter what order you put things in, you have to make sure all the molecules will wind up being in their own, in their own individual fraction by the end of your procedure, okay? And you need to be specific and make sure that those steps will work the way you planned them to. Okay, I'm going to stop this video here, and we'll do the questions 5 and 6 on the next video.